Yes, sir. It's audible.
Okay. So welcome you all to the first session of day 2 of Gyan course, Resilient Control of Cyber-Physical Systems. So since the participants are joining, we can wait for another minute before proceeding to the today's sessions. May I request the student volunteers of this Gyan course to please post a message in the WhatsApp group so that the participants can quickly join to the sessions. Anyway, welcome you all again to the day 2 sessions. So if you refer to the schedule of day 2, you can find that today 2 phases of lectures have been scheduled, followed by tutorials. So in the first phase, the lecture will be delivered by myself only. And in the second phase, the lecture will be delivered by Dr. Roshni Maiti from IIEST Shibpur. So in the first phase, let me share you the screen and please let me know whether my screen is visible or not. Can someone please confirm whether the screen is visible?
Yes, sir. It is visible.
Okay, thank you. So in the first phase, 3 different modules, or rather the topics will be covered. So we will start with the cyber physical systems architecture, followed by different stability notions and the Lyapunov approaches. Then we will have a active disturbance rejections controls and its requirement in the CPS framework. So let's begin with the architecture of the cyber physical systems. The content of today's lectures have been prepared to create the foundations of this course so that in the next 3 days lecture, we will get more ideas about the resilient control of the cyber physical system, following different types of control methodologies, stability analysis, and many more, which are listed in the schedule. So, before we go into the identifications of the CPS architecture, let's quickly review the word revolutions. As we all know that we are going through an era of industrial revolutions. So this is the era of industry 5.0 revolutions. May I request the participants to please mute their self. May I request the participants to please mute their self. So India is actively digitalizing in the power grids with initiatives like smart grids, digital substations, different types of smart meters deployment with an aim to improve efficiency, reliability, and sustainability. So if you go back to the different phases of these industrial revolutions, we are starting with the industry 1.0 to industry 4.0, as you can see in the slide, and the next paradigm shifting towards the industrializations is the industry 5.0, which is mainly a value driven phase, while the industry 4.0 was driven by the technology or policy to make digital transformations. So in this context, I can place an examples that the power grid has commissioned the world first 400 kV shunt reactor with natural ester oil at Maithon substations, West Bengal, which clearly shows the kind of digitalizations we are going through. Now, as far as the industry 4.0 and 5.0s are concerned, in which the cyber physical system is acting as a backbone, emphasizing collaborative operations between the humans and machines for sustainable and efficient manufacturing. The community of the practice 5.0, which is more precisely known as COP 5.0, was officially launched on 16th November 2023 as a starting of the industry 5.0 phase. Here in the slide, you can find that industry 6.0 is also marked, which is expected to evolve by around 2050 with an aim to achieve fully integrated and intelligent frameworks that can operate autonomously. So here is a, you can see how the revolutions takes place starting from the 70-80 industry 1.0 to the present era industry 5.0. Now, as I mentioned that as far as the industry 4.0 and 5.0s are concerned, the cyber physical systems is performing as a backbone of these two industrial revolutions phases. Now, if I suppose to define the cyber physical system architecture, it is clearly visualized that it offers a tight coupling between two different phases through a two-way communications network. The one phase is considered as a physical phase or perception layer, and the second phase is considered as a cyber or computing layer. Now, these two phases are integrated with the two-way communications medium. Now, as far as the applications of the cyber physical system is concerned, it has a vast domain of applications starting from the aerospace, smart cities, power systems network, autonomous vehicle, medical sectors, and many more. So it is obvious that if we want to make our system smarter so as to achieve a good margin of reliability and stable operations, then we have to go with this cyber physical systems framework. Now, the distributed nature of the cyber physical system, which incorporate multiple systems, for example, IoT devices, robotics and automations, different types of impressive technologies, for examples, AR, that is an augmented, virtual, or mixed reality, which represents a major shift from the traditional hierarchical automation process to the cyber physical systems architecture. So as you can see in the slides, that it clearly shows how this traditional hierarchical auto automation process has been shifted to a cyber physical domain so as to make the systems more reliable and efficiently operate under this complex environment. Now, here I have taken a reference from this particular web page, which actually defines what cyber physical systems are. So as you can see that the cyber physical systems are basically considered as a feedback systems that are networked or distributed, adaptive and predictive. It has intelligent one and must operate in real time. You can further define the cyber physical system, which you have taken into as a feedback system, possibly integrated with the economics, integrated with the human in loops. The best example is the healthcare sector, which is known as cyber physical human systems, and environment in loop. Cyber physical systems, what are the requirements for this? The cyber physical systems require cyber security, safety, improved digital tools, and different advanced design methodologies. Now, the cyber security is basically comprises with these following attributes, which are resiliency, privacy, malicious attacks, and intrusion detections. So if you go into the state of the art of the cyber physical systems architecture, you will find out two important attributes which have been interchangeably used for demonstrating the importance and acceptability of the CPS framework. One is the attack detections approaches, and then the defending algorithm through which we can ensure high degree of resiliency of our network assisted smart system. Now, the cyber physical systems have different applications, as I have marked and stated before, that it can be used in the communications purpose. It can be used for the energy field, infrastructure field, healthcare field, manufacturing fields, and many more. So this is a simple CPS tree through which all the important attributes of the cyber physical systems can be defined. Now, how do I validate whether my cyber physical system is acceptable by the users or not? That can be done through the simulations and or real-time demonstrations. So as you can see, here it is marked, and scalability and flexibility and achieving high degree of resiliency showcases the wider range of applications of cyber physical systems in this complex network assisted world. Now, here in the slides, you can find the architecture of the CPS is basically governed with 3C components. One is communications, followed by computations and control. So if I go back to the previous slides, as I marked here, that the cyber physical system architecture is basically comprises with the three different layers. One is physical, where we have our real-time objects like actuator or the measurement devices. Then we have a cyber or control layer where we have to do our controller designs through some software development, algorithms, etc. And these two layers must be connected with the communications medium. So that finally define the architecture of the typical cyber physical systems. So here the three C's are communications, computations, and control. And as I marked that it actually has a three different layer followed by an human interface is also there. Basically, in the applications of cyber physical human systems, the best example is the healthcare, where you can have a human interference in this cyber and physical domains. So actually you have a four different layers in the CPS architecture depending upon its framework and applications. Now come to the functionality of these three different or four different layers which were stated in the previous slide. So physical layer, where you actually have a plant dynamics. So whatever the plant dynamics you have in the real-time domain, that you can describe mathematically, or you can develop the simulation model as much as you can in this domain. Definitely under certain valid assumptions. Now this physical layer basically collects the real-time data from the processes or system through different IoT measurement devices. Like if I refer to the smart grid, then the phasor measurement units is there in the physical layer, which records the different measurements of the power systems unit. And then once these data are available or the measurements are available with us, those measurements will pass to the computations or cyber layer through a communications medium. So just to make an interfacing between this cyber layer and physical layer, different types of communications protocols are available in the state of the art depending upon the architecture of your CPS and applications. So few are listed down here. For examples, you can have a communications between the physical and cyber layer through the Wi-Fi. One of the best example is the monitoring of UAV in a given area. So monitoring of an area with the help of a UAV. So where the sensors or the cameras, these are mounted in the physical unit or deployed in the physical unit. Those records the environment like videos capturing or image capturing, whatever be it as per your requirement. And those informations once collected from the physical domain will stored in the cloud, and from the cloud you can further fetch those informations in your cyber layer so as to perform necessary computations in order to monitor and control your physical system. So this is how the communications takes place. So you can have your communications through different protocols like Wi-Fi or other as per your requirement. And then we have a cyber layer where you have to do your computation task like software development, design of a controller, and based on this control algorithm, whatever the necessary signal that you have generated will again pass on to the physical layer for controlling and monitoring the physical objects. Now, if I refer to the state of the art of the CPS keyword, we will find out two attributes are interchangeably used in different state of the works. One is the cyber physical system itself, and the second one is the IoT. So IoT is often correlated or compared with the CPS, but we have to be very careful while we are defining these two words related to our own applications. As far as the North American industrial sectors are concerned, they are mostly defining their systems with cyber physical systems, while the European industrial sectors, they mostly use the keyword IoT. Now, as far as this Vanderbilt University, United States is considered, they have clearly defined the differences between these two smart words. One, IoT, which actually creates a network between the different interconnected devices, what you can call as intelligent devices, so as to collect and exchange the data or measurements. While this, with the help of CPS, what we can do, we can monitor and control the physical processes in a seamless manner against different types of unknown inputs to the physical system. Now, as I mentioned before, that the two tasks that we have to take into consideration as far as the CPS study of CPS framework is concerned. One is the detections of malicious attacks or inputs in the physical systems, and the second one is the development of a resilient, cyber resilient algorithm so as to increase the defending power of the physical systems towards different types of unknown inputs in the physical systems. So if you refer to the definitions of the cyber resiliency in the state of the art, it clearly defines, or rather it quantifies, the ability of the physical systems to withstand and recover from network threats, ensuring the stable operations with minimal disruptions from the desired output. Now, as I told that to make an interfacing between the cyber and the physical layer, we have to go through different types of communications protocols so that a seamless connections can be established between the physical and cyber layers in a given operations. So few of the protocols are mentioned in today's presentations because of the limitations of the available time. However, if one is interested to get more about the detailing of these communications protocols, they are they are requested to refer to the available state of the art works. So we are starting with the IEEE 802.15.4, which has been extremely used in the smart grid applications. This standard is basically defines the low rate wireless personal area network through which low power, low data rate and reliable communications over a short distance can be established. Next, we have another communication protocol, which is IEEE 802.11. Basically, it is defined as a wireless LAN standard, WLAN standard. So that actually help us to broadcast video or any images in real time. So one of the example is the UAV to the pilot communications. So if I want to ensure the UAV to the pilot communications, then I can easily use this type of communication protocol in my real-time operations. Sorry. Then we have another different communications protocols used in the smart grid communication network, starting with the Modbus, which is established as a master-slave communications between intelligent electronic devices, what is called as IED. So just to make a communications between different IEDs in 1970, this communication protocol was derived by the Snyder's Electric, which is famously known in today's times. Schneider Electric, they actually derived this Modbus communications. That time, they were defined it as a communications medium between master and slave. Now in 2020, this master-slave keyword has been replaced with the server-client keyword. So this has been extremely used in the real-time operations. Then we have a distributed network protocol, which is used in the smart grid systems. This DNP3 is primarily used in the SCADA systems for making a communications between the master stations and different RTUs. Then we have IEC 61850, which is also used to ensure the communication between IEDs, intelligent electronic devices. That also ensure the seamless communication between different IEDs. ZigBee is another communication protocol, which is a wireless protocol derived based on this ID that actually ensures the seamless communications between different smart meters used or deployed in the smart grid stations. Then we also have a communications protocols for the autonomous vehicle operations. So as you can see in this diagram, we can have a communications between vehicle to vehicle. We can have a communications between vehicle to sensor, vehicle to infrastructure, vehicle to persons, and many more. So as far as this application domain is concerned, so few communication protocol are listed in the slides, starting with the LIN, local interconnected network. Then we have a CAN, controller or campus area network. Then we also have FlexRay, which also used to ensure the vehicle to vehicle communications. So this type of communications protocol can be used in the applications where V2V or V2S or V2P is required. So I mentions again that we have listed down only few communications protocols. Those can be used in the CPS framework operations. However, if we want to get more exposure about the communication protocols related to our own applications, we can definitely refer to the different reported state of the artworks. Now, the next questions obviously comes in our mind, why, sorry, what are the different areas of applications of CPS in today's time? Although I have mentioned previously that it is starting from the smart manufacturing systems, following the healthcare and medical systems, power grid sector, autonomous vehicles, and many more. So I like to say, or I like to record this statement that if I want to make my system more smarter so as to achieve high reliability and resiliency, then I have to definitely go with the CPS architecture. I have to derive or design my systems in CPS architecture so as to achieve great level of flexibility, great level of reliability, and ensuring our seamless operations in the complex network. So here you can see schematically the applications of CPS, or the what I can say, the deployment of the CPS framework in the healthcare systems is pictorially depicted. So that is a big area where the CPS systems can be further explored. We have applications in the autonomous vehicle sections where we want to make a smooth communications between the vehicles. And of course, in all these respects, one more keywords can be considered, and that is the multi-agent systems. So multi-agent system is basically a network assisted systems where you can have your great exposure related to the cyber physical systems. We have a smart grid because the power sector has gone through a digitalization phases where the CPS plays a great role. Now, obviously, while we talk about the open communications network through which the physical and cyber layers are interconnected, this open security, the ensuring the security of the system is suffering with a great challenges, because this open communication network is readily available to the cyber criminals who can access your systems and mislead your operations, mislead your measurements, mislead your control signals, and finally can drive the systems to instability. So it is obvious that although the cyber physical architectures offers a good flexibility, good resiliency, and efficient operations in this complex network, but it is vulnerable to different types of prominent network threats, because the communications medium through which the measurements, either the measurements or the control actions or control command transmitted either in the cyber layer or in the physical layer, which is open to the cyber criminals, and they can easily access that communications medium so as to disrupt the nominal operations of your systems. So ensuring the security of the cyber-physical system is a challenging task to the CPS engineers, and a continuous research is going to improve this, or rather to improve the security of the CPS platform. Now, although it is there in the schedule that we will go through the different types of cyber attacks in detail in the subsequent lectures, but just to have a quick review and to establish the importance of the security aspects of the CPS system, let's quickly review different types of attacks appear in a network assisted physical systems. So this tree is basically defines the different types of attacks can be encountered in your systems during the real-time operations. Among these types of attacks, few are more prominent network threats which disrupt the nominal operations of the systems at a great level. So those prominent cyber threats will be quickly reviewed in today's presentations, and their impacts on the nominal operations or the stable operations of the systems will be demonstrated through some numerical examples in today's discussions. So we are starting with the two prominent attacks. One is deception attack, or in the state of the art, it is marked as a false data injections attack or bad data injections attack. There are two possible locations where this type of deception attack can be introduced in your CPS system by the cyber criminals. One is at the measurement end, and the second one is at the actuator end. So here you can see schematically the CPS network is demonstrated. So here is your physical system, what we called as a perception layer or a physical layer, from where the measurements are taken by the sensors, and those measurements are passed through a network to the control master controller or a control center, whatever we can call. And again, this controller generate the necessary control actions to the actuator, and that actuating signal is finally driving the plant operations. Now, this type of deception attack can be appeared at the sensor end, or it can be appeared at the actuator end. The objective is very simple. The objective of injecting this type of deception attacks either sides of the cyber physical network to mislead the signals, either measurements or the control effort, by introducing some false data injections or by making the sensor end jam or block. And the same thing that we can do at the actuator end, working as a cyber criminal. So this type of attack offer a destructive outcome, because if you have a wrong measurements, if you collect the wrong measurements, or if you send the wrong measurements to your cyber layer or a controller, to control these physical systems, definitely we will not get the desired actions. That means this wrong measurement mislead the controller to generate the wrong control actions so that this physical unit goes out of the stability. That is the main objective being a cyber criminal. And the same thing that we can do at the actuator end, we can falsify the actuate the control law by injecting some unknown inputs or unknown signals so that the control signals can be magnified, or maybe it is not sufficient to drive the actuator, and finally the operations of the physical systems goes out. So this is one of the important challenges that we have in the CPS operations. And of course, we have to deal with this type of attacks because they are completely unknown to us. If they are detectable, if we can able to derive some detection algorithm so that this type of false data injections can be well detected beforehand, then definitely the control actions can accordingly be manipulated so that the stability of the physical systems can retain. If it is not detectable, then we have to ensure the resiliency, cyber resiliency of the controller to a great level so that the stability of the systems will at least retain while this type of events appear in our network. Yes, definitely. While this type of unknown inputs will appear to the systems, the system performance may slightly deteriorate. So that's why we have defined the resilience in that way, that a controller is said to be resilient if it is withstand, or a control system is said to be resilient if your control system is able to withstand and recover against this type of unknown inputs. So this is the first type of attacks which is extremely available in the CPS network. Another one is the actuator cyber attack, which I also mentioned. The objective is to make or falsify the control actions. Maybe you are injecting some signals because of which your control signal is significantly magnified. That may cause to the actuator saturation and your system goes out of the stability. So that is also possible, or rather that is the main objective of injecting the actuator cyber attack by the cyber criminal. Another class of cyber attacks attack which we frequently appear in our network assisted system, what is called as DOS attack, denial of service attack. So you can clearly consider this type of attack, or rather you can compare this type of attack with the real-time example, what is traffic at a given signals. So the objective of the cyber criminal to introduce the DOS attack into the network assisted system to block or jam the communication channel for a period of time. So you can think about that you are intentionally creating some delay while you are communicating either measurement from the physical to the cyber layer, or while you are transmitting the control signal from the cyber layer to the physical layer. And we know that the delay always offers an adverse effect as far as the system dynamics and the stability are concerned. So with this intentionally with this intentionally making blocking or jamming in the communication channel may cause the instability issues, or maybe your systems will not able to offer the desirable operations, and you will not get the actual performance from the systems. So this DOS attack can be sequentially introduced in your communication channel, or maybe it is asynchronously generated in the communication channel. So pictorially, the DOS attack, which I have taken from the state of the art, can be categorized with two different components, what is known as jamming period and sleeping period. So as you can see in this diagram, this, for example, this is the total period of DOS attack. Capital T is the total period of DOS attack. So out of this total period of DOS attack, this period of time, the DOS attack is in sleeping mode. It makes the sense that we are ensuring a seamless communications or data exchange between the cyber and the physical layers. Now, during this period of time, when the DOS attack is active, that makes the sense you are blocking the communications medium so as to disturb the nominal operations of your network assisted system. So that is the main objective. You are creating an intentional delay, why making block or jam the communications medium. That means you are not allowing the data to transfer either from the cyber to physical or physical to the cyber layer. It's up to you only, or rather it is up to the cyber criminal whether they are interested to block the measurement data, or they are interested to block the control signals. In both the way, they can definitely disturb the nominal operations of the systems. So to account or to counteract those types of unknown inputs in the network assisted systems, you have to have a very high control algorithm in the cyber layer. High control algorithm in the sense, we have to have a very intelligent and resilient control algorithm in the cyber layer, so that at least we can ensure the system stability while these types of attacks appears in the network. Now, another class of another class of cyber attacks, which is available in the literature, what is called as distributed DOS attack. Although it is sound like a DOS attacks, and the objective is also very simple, the same objective that the cyber criminals have, they want to block. But here in the DOS attack, what we can do, we can access the communication medium through a single source only. But in the case of distributed DOS attacks, what we can do, we can have a multiple sources in our hand as a cyber criminals, and through which we can block the communications medium. So your communication channel becomes heavily trafficked because of the injections or the deployment of the distributed DOS attack in the communication systems. So be careful while you are dealing with the CPS architecture, that your architecture may be injected with a DOS attack from a single source, which can be quickly managed because of the advancement of the computing operations and parallel operations of the digital systems. But dealing with the distributed DOS attack is a challenging task, because your communication medium is continuously injected with this type of DOS attack from different sources. Even the cyber criminals, what they used to do, they create some virtual puppet through which this communication medium can be accessed and the attack signals can be injected. So in the case of distributed DOS attacks, your attacker is basically operated in a pseudo sense. You won't be able to identify the attacks, because continuously the signals, this unknown delay signal, is coming from the different sources. So handling this type of distributed type of cyber attacks is a challenging task, and it opens further research in the respective field of applications. Now, beside these three different types of attacks which normally encounter in our practical applications. We can have another classes of or another groups of network threats. For example, packet data loss. uh, you can have what is called time delay switching attack, spoofing, and many more are there. So few of them are listed down here, and their descriptions are also mentioned. So I'm not wasting the time to read out all these different types of attacks. One can easily refer to the literature to have a good essence of it. But the objective of this slide is that although these three different types of attacks which we have discussed, and in the subsequent phases, the simulations or the numerical examples that we have solved and prepared in the slides will follow these type of attacks only. So a detailed discussions of these deception and DOS attacks have been carried in these presentations. So before we go into the further discussions, I welcome few questions from the participants' ends. If the participants have any queries, I will be happy to answer those queries. Is there any query from the participants' end? Is my voice audible? Is my voice audible?
Yes, sir.
Okay. So if there are no queries, we can proceed further. So as you can see the title and the content of this Gyan course, we are mostly emphasizing towards the uh, development of resilient control algorithms so that the stability, robustness, along with the good shaping of system performance can be achieved when my system is subjected with different types of unknown cyber threats. So being a systems learner, we know that when we talk about a control system, especially the feedback control system, because I mentioned that the CPS is a feedback control systems only. So while we talk about the feedback control systems, three important attributes that we have to fulfill so as to ensure the acceptability of my designs. The first is the stability. I have to ensure the stable systems in all respects. The system must offer a good dynamic responses. Whatever the dynamic responses you are looking for, your system must offer that good dynamic responses, and definitely the robustness towards the different types of uncertainties. Here you can think about the uncertainties in the structural form, or maybe the uncertainties in the unstructural form. What is interchangeably used in the literature as matched uncertainty and unmatched uncertainty. So matched uncertainty is basically defines when the unknown disturbances appears in the same control channel through which the control signal is applied to the plant. I hope my point is clear. I repeat, there are two types of uncertainties which are interchangeably used in the literature. One is called matched uncertainty, and another one is the unmatched uncertainty. What is this matched uncertainty? So suppose we have a system dynamics x dot is equal to a of xt. Let's take a linearized systems to define the definitions. A of xt plus, we know that the second part is the bu of ut. Now suppose This is the control channel through which the control law is fed to the plant. And if your disturbance is appeared in the same control channel, so your dynamics will become B into U plus D. Let the D is a function of time. It could be a function of state also. So in that case, you can call that uncertainty or the disturbance as a matched disturbance or matched uncertainty. Or you can have your disturbance as an unmatched form. For examples, the system is described something like this, where you can think about that this theta is basically a disturbance component which not necessarily appears in the control channel. It is appeared in the plant, either in the measurement or you can have a internal variations also, internal parameter variations also. Maybe you can think about unmodeled dynamics, which are also unmatched uncertainty. Different type of strict nonlinearity we have in our real-time systems. Those can be considered as an unmatched uncertainty. Anyway, so you have to ensure the robustness of your physical system, whether it is network assisted or not network assisted, but the robustness toward the uncertainties has to be guaranteed at the end of your designs. So these three important attributes that we have to take into account while we talk about a feedback control systems. So CPS, the design of a resilient control system, is also not different from these aspects. Anyway, we will have a detailed discussions on the stability notions in the second part of the lecture. But quickly, just review the attributes which we have, starting with the very well known bounded input, bounded output stability, which is mostly applicable, or rather we talk about the Bibo stability when we are dealing with the relaxed systems. But so far the real-time system is concerned, we always have certain initial conditions. So mostly we talk about the asymptotic stability while we're dealing with the real-time systems or real-time control systems. Then we have an UUB stability, what is known as ultimate uniform bounded stability, exponential stability, and the last one is the input to state stability. So it's up what type of stability that we are going to ensure at the end of the designs is totally depends on my designs and the problem statement. If I'm dealing with a simple relaxed LTI systems, then at the end of the design, I need to only ensure the Bibo stability. Okay. If I'm dealing with a practical system where initial states are defined, then I have to ensure the asymptotic stability. Although it is hard to achieve in the real times, so the people usually describe or rather people used to only mentions the UUB stability of the real-time plant. So this is certainly repetitions of the definitions of the resiliency, which I mentioned many times in the discussions, that ultimately we have to ensure the system must withstand any type of disturbance inputs. It could be a disturbance coming from the environment in the form of cyber attacks, or maybe the disturbance originated internally. And your system must be recovered from that deviations and return back to its normal operating situations. Now, quickly review different types of cyber attack recently happened in our real-time world. So few are listed down in these presentations. So you can see one of the cyber attacks in the Ukraine power grid in December 2015. That has a great impact in the Ukraine power network, and 30 substations were switched off and about 230,000 people were left out with the electricity for a period of 1 to 6 hours. So that has a great impact. Another example which I have taken from the state of the art, that is a 2009 Iranian nuclear enrichment facility cyber attack. Here also, the PLC's units were stopped and the nominal system operations were disturbed. So some are listed down here also. For examples, in India in 2019, the attacks appears in the nuclear power plant, and many more are there. So as I told, although CPS makes your system flexible, ensure efficient operations, but upholding the security against the cyber threats or the network threats is a challenging task. So I have to ensure the data privacy. I have to ensure the resiliency so that the nominal operations of the systems will not disturb to a great extent. So advantages of CPS, I mentioned many times, and the disadvantages of the CPS is it requires a very robust cybersecurity strategies. So your control algorithm must be intelligent enough so that any type of disruptive events will not cause the failure of your systems. It requires a high end of designs knowledge, implementations and maintenance cost is also relatively high. However, uh, considering its flexibility and efficiency operations, it also reduces human interventions. The CPS has been greatly deployed in different practical applications. Now, at the beginning, I told that today's lecture is formulated with some basic ideas of the control theory, especially the stability analysis, because not only the real time, numerically also or qualitatively also, we have to ensure the stability of the cyber physical systems under the developed control architecture. So performing or doing the stability analysis is also an important part of the research and the study. So the second part will explores different stability notions. Few of the stability notions I have uh, read out in the previous slides. However, their definitions, their importance, their applications, and how one can proceed to perform qualitatively stability analysis with the help of famous Lyapunov algorithm will be explained in the second part of today's discussions. So if you have any query, you can place your query. As of now, is there any query from the participants end? Thank you. So this is a very famous mathematical attributes uh, frequently used when we go for the qualitative analysis of the control system, step qualitatively analyzing the stability of the control system, feedback control system, what is called as Lipschitz continuity or Lipschitz functions. So this is the statement of the Lipschitz functions. We are considering an autonomous non-linear system. So it is a non-linear system. It is not a non-linear control system. F is a non-linear function and which is a function of the state only. As you can see in the argument of F, U is missing. So we are calling it as a non-linear control system. Sorry, non-linear system, not the control systems. And F is not explicitly dependent on time. Yes, X is the state variable or a state vector, which is a function of time, but F is not explicitly dependent on a time or described with time. So we are calling this type of description as a description of an autonomous system. And of course, it is a non-linear one. So which says a function, something like this, is said to be local ellipsis or hold the ellipsis continuity if these two criteria are met. Number one, you can choose a ball, neighborhood of the functions, and you have to take the tangent at that ball to the extreme 2 points of the ball, and you have to make sure that this norm, which is an Euclidean norm, is less than this value. This capital L is called the ellipsis constant. Now, here one example is given to you. For example, suppose you are dealing with a function which is something like this: fx is equal to x to the power of 1/3. So fx1 and fx2, basically you are calculating this derivative of this function at two different points, x1 and x2, or you are performing the computing the tangent at two different points, x1 and x2. So if I go into the calculation of that, so what I can see that this derivative is coming out to be something like this. Whatever be my x1 and x2, x1 and x2 are the 2 points about this x0. So what you can think about, suppose this is your x0. Suppose this is your x0. So you have taken a very small ball about this x0 points, and these two extreme values, at these two extreme values, you have taken the tangent of the given function so as to check whether your function is local ellipsis or not. So the plot of this function is available here. So you can see that at x equal to 0, so if you put x equal to 0 in these equations, this becomes undefined. So at x equal to 0, these functions is not satisfying the ellipsis continuity. So it may be local ellipsis everywhere except x equal to 0. So what you can say, yes, fx is local ellipsis everywhere in the x except x equal to 0, because at x equal to 0, this ellipsis continuity violates. And this is the one of the foundations for performing the stability with the help of Lyapunov approach. Now, before we go into the formal definitions of the Lyapunov approach, quickly review some different classes of functions based on which the Lyapunov mathematical descriptions of the Lyapunov is formulated. So we are starting with the class K functions, following class L function, and then class KR functions. One, if one want to get more detail about this Lyapunov study and this type of functions, they can refer to the two different references. One is H.K. Khalil and the second one is the Vidyasagar book. These two are the very famous book of nonlinear control theory. So a function is said to be class K functions if it is continuous. Continuous means at every point you can ensure the ellipsis continuity. It is a strictly increasing function and phi 0 is equal to 0. So class K function is basically associated with the local stability attributes. We will come in the next slides. But class K, if you ensure your function is a class K functions, that means you can ensure the stability of the systems in the sense of locally. Class L, a function phi, which actually map from any real positive number to another real positive number is said to be class L function if it is continuous, strictly decreasing, and phi 0 is a finite quantity. So this class L is associated with the global stability notions. And another function class is there in the literature, what is called class KR functions, a function phi in the same line, which actually maps any real positive number to another real positive number, is said to be class KR functions if it is a class K functions and phi for any value of x is tending to infinity, as that value is tending to infinity, what is called as radially unbounded condition. This is called radially unbounded conditions. So you can define your class KR as a function is a class KR function if it is a class K function inherently and radially unbounded. So this type of class KR function is actually related with the global stability. This is not global stability. This is called uniform stability. Class L is associated with the uniform stability. Class K defines the local stability and class KR defines the global stability. Global stability means you can ensure the stability of the systems anywhere in the state space plane. So two things that we have to fulfill. One, the function should be a class K function and it is radially unbounded. Why we are going all these type of classes of functions? Because the Lyapunov stability, the mathematical tool which we are frequently used to demonstrate the stability of any feedback control systems, non-linear feedback control systems, that rely on the choice of the Lyapunov candidate. The Lyapunov candidate, while we are choosing the Lyapunov candidate must be chosen considering these three different classes of functions. So we have to choose a Lyapunov candidate for a given system so that at least we can ensure the local stability, uniform stability, or global stability. It is totally decided by the choice of the Lyapunov candidate. So that is why this introductory slide is presented before all of you. Now, let's come to the formal definitions of the Lyapunov theorem. See, while you are defining the stability of any system, of feedback control systems, with the help of Lyapunov theorem, we normally call that stability as a stability in the sense of Lyapunov only. It could be a local stability, it could be uniform stability, it could be global stability, or any other type of stability. But as you are concluding or performing the stability analysis with the help of Lyapunov theorem or Lyapunov argument, so the stability is to be defined in the sense of Lyapunov theorem only. One more thing which I missed out, that is, while you talk about the stability of a nonlinear system, the stability is to be defined with respect to the equilibrium point. Although mentioning whether the system stable or unstable is quite easy in the case of LTI system, because in LTI system, although it is an idealized assumptions, in LTI systems, we don't go for the calculations of the equilibrium point again and again, because we know that the system has a single equilibrium point and that is the origin if it is a free systems. So obviously, because we are talking about the asymptotic stability, so we no need to go for the precise calculations of the equilibrium point. But nonlinear systems, suppose the system is described with this type of differential equation x dot is equal to fx, it might have a multiple equilibrium points. For example, a pendulum systems. If you refer to the pendulum dynamics, it is a second order dynamics and it actually holds two equilibrium point. One is the 0, 0 equilibrium point and the second one is the pi 0 equilibrium point. So a nonlinear system may be having more equilibrium point. So it is up to you, okay, based, it is up to you, okay, how will you define the stability of the system, whether it is the definition with respect to the 0, 0 point or it is a definition with respect to the pi 0 points. So this thing we have to keep in mind while we are dealing with the non-linear dynamical systems. So let's for this particular systems, we have taken a Lyapunov candidate. So this is the Lyapunov candidate, which is an energy-like functions, b of x comma t. B may be a function, x is a state in this case, and t is the time. If your system is not explicitly dependent on a time, you can choose your Lyapunov candidate only as a function of state. But if you have a non-autonomous systems or you are dealing with a non-autonomous system, then you have to choose the Lyapunov candidate as a function of t also. So this vxt, we are calling it as a candidate Lyapunov functions, which actually map the state and the time from a domain D to a real plane R. So it is a vector quantity because state is a vector. But while you are mapping these states with the help of this Lyapunov candidate, it actually gives you a scalar quantity. So this actually shows the mathematical representations that this Lyapunov candidate is defined as a function of x, state and time, which maps anything from a domain D to a scalar quantity R. It is supposed assumed to be continuously differentiable and positive definite. That is actually demonstrated by this inequality conditions that you have to choose your Vx Lyapunov candidate to perform the qualitative stability analysis that must hold this inequality situations, that it must be less or equal to W1x and greater or equal to W2x, where W1 and W2 are two time independent positive definite functions. So the first inequality defines that your Lyapunov candidate is a positive definite functions, and the second inequality defines your Lyapunov candidate is a decrescent function. Decrescent function means that its derivative is a non-increasing function. If I go for the calculations of the directional derivative, because that is the main foundations of the Lyapunov stability. So the first step, you have to choose a Lyapunov candidate which follows this inequality, that is a continuously differentiable function. It must be a positive definite function and a decrescent function. And if you find out the directional derivative of this Lyapunov candidate or Lie derivative of the Lyapunov candidate, because v dot x comma t, that means you are finding or you are doing the differentiations of this Lyapunov candidate along the state trajectory only. If this directional derivative is less than 0, then what you can say, your system, this system is locally asymptotically stable at this equilibrium point in the sense of Lyapunov. I repeat, if the directional derivative of the Lyapunov candidate comes negative semi-definite, then what we can conclude that the autonomous system which we are dealing is locally asymptotically stable in the sense of Lyapunov at that equilibrium point. Why it is locally? Because you have taken the mapping from a domain D to domain R. So if you choose your Lyapunov candidate Vx comma t, which map anything from a real plane Rn to real plane R, then the same definition under these situations, that this directional derivative is less than zero, we can call it as a globally asymptotically stable. So it is totally decided whether you are talking about a global stability or a local stability, although the local words and global words are associated with the attractiveness of the equilibrium point, whether your trajectory eventually attracted to the equilibrium point or converged to the equilibrium point or not. To address that situations, these local and global words appear. However, we are merging. While we talk about the asymptotic stability, we are ensuring that the trajectory is bounded. Not only bounded, it is converged or attracted to the equilibrium point. So this is how these two definitions can be differentiated. As you can see that the word local or global is decided by the choice of the Lyapunov functions, whether this Lyapunov functions maps anything in the plane, in the domain or a ball D to R, or it is mapping from anywhere in the state space to a scalar quantity R. Another way we can decide the local and global stability, if your Lyapunov candidate is a class KR function, if you can make sure that your Lyapunov candidate, whatever the Lyapunov candidate you have chosen to perform the stability, which falls under this class KR function category, then it makes the sense it is a global asymptotically stable. You are talking about the global asymptotic stability of the equilibrium point of the given autonomous system. That means only one more thing that you have to ensure, that whatever the Lyapunov candidate you have taken, so V of x comma t, that is the Lyapunov candidate I have taken. If I find its Euclidean norm, and if it is tending to infinity, as norm of x is tending to infinity, that makes the sense your Lyapunov candidate is also radially unbounded. That makes the sense it is radially unbounded. So if it is radially unbounded, then definitely this global stability will ensure for the given system. But all these definitions from the perspective of the Lyapunov only. So we are defining the stability whether it is global or a local in the sense of Lyapunov. Now one more stability notions I have marked over here, what is called as uniform stability. This is very easy to answer by the just emphasizing to the dynamics of the systems. If the right sides of the dynamics is not explicitly dependent on time, by default it becomes an uniformly stable. That means your Lyapunov argument is only a function of state, it is not a function of time. You no need to have a dependency on a time, it is independent on a time. So that makes the sense it is uniformly stable. So only look or just see whether the dynamics is a function of time or not. If it is a function of time, then yes, it is not uniformly stable. If it is function of not a function of time, then you can directly comment, okay, yes, it is uniformly stable. So some pictorial demonstration is also given, although these all are the very foundational attributes for a control system students. So if those who are not from the control system background, participants, those who are not from the control system background, I request them refer to this Vidyasagar book or Khalil book, nonlinear control theory book, to have a more exposure about the stability notions. So all these points I have discussed. These are simple the mathematical uh, discussions or this formal definitions of the stability. We have talked about the uniform stability. Just I have to check whether my system, the dynamics of the system, right side component is a function of time or not. If it is not a function of time, then directly it is an uniformly stable. Then we have to go for, of course, it is after the calculation of this directional derivative only we can comment. If it is less equal to 0, the directional derivative is a negative semi-definite, then we can ensure that it is stable. If it is strictly negative definite, then it is asymptotically stable. Or if the directional derivative is positive definite, that makes the sense it is unstable. Unstable means your trajectories goes out from the ball or the domain within which you are performing your analysis. Now, here one examples I have taken from the Vidyasagar book, which actually defines the attractiveness and the stability. So a second order dynamics is given. So as you can see, the right sides of these differential equations, both the differential equations is not explicitly having a time component. I repeat, the states may be a function, they are function of time, but the differential equations, this f of x nonlinear argument is not explicitly having any time component. It is only a function of states. So uniformity is ensured. Just looking the system dynamics. Now, if we go for the phase portrait of this nonlinear system, I can have the phase portrait maybe something like this presented in this figure. So as you can see, if you choose any initial condition within this confined zone, any initial condition, if I choose within this confined zone, the trajectory goes out from this red ball and the blue ball and eventually converge to the origin. Actually, this is the stability what we defined in the sense of epsilon delta definitions. So what they say is, if you choose any initial conditions, any initial state trajectory condition within this delta ball, the red ball, if you are ensuring that the trajectory will remain within this epsilon ball for all future time, that makes the sense it is a stable system. If the trajectory goes out of this blue ball or epsilon ball, then the system at that equilibrium point is said to be unstable in the sense of Lyapunov. So as you can see in this example, whether you have taken the initial condition within this red ball or somewhere outside of the red ball, as far as this portrait is concerned or the trajectory is concerned, the trajectories goes out of the blue ball and eventually converge to the equilibrium point. So what you can say that yes, the equilibrium point is attractive, but since it's violate the epsilon delta definitions of the Lyapunov stability, the equilibrium point is not a stable equilibrium point. So attractiveness doesn't imply the stability. It is, if I am dealing with the Lyapunov approach, then I have to refer to the definitions of the epsilon delta stability so as to guarantee the stability under any initial conditions within the D ball or anywhere in the space, depending upon whether we are talking about the local stability or global stability respectively. So this part I have already discussed. Okay, if you choose a delta ball or you are ensuring this Lyapunov candidate, if you have chosen the Lyapunov candidate to map from a local ball to a scalar quantity, then it is a local stability. And if you ensure that this is a class KR function, then your stability is a local global stability globally stable or globally unstable depending upon the signs of the or the definiteness of the directional derivative. So here is another examples, very famous examples, a van der Pol oscillator whose dynamics is given. This is a second order systems, any type of stable uh, any type of oscillator that we are using in the real-time applications follows this type of limit cycle property. So here also you can see that this is the delta ball, this is the delta ball, and this is the this delta ball may be somewhere here. You can choose a delta ball somewhere here nearby of the equilibrium point. So, and this is the epsilon ball. You can call it as an epsilon ball. So what it says, this van der Pol oscillator, it exhibits a limit cycle phenomena. What this limit cycle phenomena says, okay, if you choose your state trajectory, the initial states anywhere in this epsilon ball, eventually it goes out of the epsilon ball and converges to a limit cycle. This is what we call as a limit cycle. So although it will not goes out of the limit cycles, okay, it will eventually converge to the limit cycle. So that means a sustained oscillation we will get, a bounded magnitude of the state trajectories we will get. But as far as the Lyapunov stability is concerned, this epsilon delta definition is concerned, we can conclude that yes, the signals are bounded, but the equilibrium point is unstable as it violates the epsilon delta definitions of the Lyapunov theorem. So another most important stability that we normally look when we are dealing with the real-time system, what is called the exponential stability. What it says, if you have a two positive constants, say alpha or beta, if we have a two positive constants alpha and beta, and if I find out the norm of this state, the Euclidean norm of the states, or norm 2 of the state, whatever. So if it is less than these conditions, it actually implies that the decaying rate of the state trajectory to the equilibrium is faster than the decaying rate of any exponential functions. So it's up to us, okay, how do we choose the alpha and beta? So depending upon the choice of alpha and beta, what we can, if we can ensure that the decaying rate or the convergency rate of the state trajectory to the equilibrium point is faster than the decaying rate of any exponentially functions, then the stability can further be enhanced as an exponential stability. So if you talk about a linear systems, simple x dot is equal to ax plus bu, stable linear systems, then the stability is always implies as an exponential stability. So the next is the UUB stability. So as I told that in the real-time practice, it is hard to achieve the asymptotic stability. So what we can ensure at least the boundedness, ultimate boundedness of the state trajectory neighborhood of the equilibrium points. If I can ensure that, then that is sufficient uh, to showcase the acceptability of the control algorithm. So instead of going into this formal definition of the UUB stability, let me go back, because one figure I have added that actually demonstrate the concepts of the UUB stability. Here also it is also defined from the epsilon delta ball perspective. So as you can see that a delta ball I have chosen here, which is marked with a blue line, and epsilon ball that I have chosen as a red line. So uniformity is clear to all of us. we can ensure the uniformity of the state trajectory by looking into the right side component of the differential equations. Now what it says, K, if I starts anywhere in this epsilon ball, so as you can see, I have started somewhere here. If I choose the initial conditions anywhere in the epsilon ball, and after a elapse of time capital T, after an elapse of time capital T, if the trajectory is bounded within this delta ball, this delta bound is called the ultimate bound. If an elapse of capital T, if I ensure the state trajectory is bounded within this ultimate bound or a delta ball, that ensure that your system at the equilibrium point is ultimately uniformly bounded. That is sufficient. So mostly while we design the adaptive control algorithms in the real-time practice, although the state trajectory, the asymptotic convergency of the state trajectories can be ensured with the help of Lyapunov approach or Barbalet's corollary, but as far as the parametric errors are concerned, the design parametric errors of the controller are concerned, what we used to do, we ensure the boundedness of those parametric errors instead of conforming whether they are asymptotically converging or not. So that is sufficient, I believe. So now next attributes which we frequently used in our designs or while we demonstrate the control system, what is called as a control affine systems. So this is the descriptions of the control affine system. So far we were discussed the system or describe the system as x dot is equal to function of x. Now we are talking about a control affine system where I am discussing or rather describing the state as a function of x and u. Of course, this u is a function of state. Let it be a function of state, f of x. F of x and u is a function of x. So this is what we call as a control affine systems. That means the system is a non-linear, but the control law is supposed to be a linearly appeared in the equations. If both states and control are affine, then the same system can be categorized as an LTI systems. So I repeat, the control appears in these differential equations linearly, while the state is associated in the differential equations with the nonlinear function f. And if you choose both states and control as a affine component, then your system is said to be a simple LTI system. And for a control affine system, we have a different notations for choosing the Lyapunov function, what is called as control Lyapunov functions. And this control Lyapunov functions has been predominantly used in the designs of a backstepping control, because backstepping is one of the famous robust control approach reported in the literature, which ensures high degree of robustness of the systems towards the disturbances or uncertainties. Then one more thing that we have over here, what is called a small control property. It is also used in the designs of the control algorithm. What it simply says, okay, if you have chosen the initial conditions close by to the equilibrium point, then the amount of control signals required to drive the system states to the equilibrium is also small. That is the important thing. I repeat, the small control property of any control law is highly important when we talk about the robust control designs. It shows that if these initial states or initial gas is nearby to the equilibrium point, then amount of control law required to drive the states to the equilibrium point is also small. If it is not satisfied, then the small signal control property of your control law is simply violated. So, do you have any queries? I can take one or two questions from the participants if they have queries. Is my voice audible?
Yes, sir,
Yes,
audible.
visible.
Okay, so is there any query from the participants end? Okay, so we are at the last part of first phase discussions, what is called as active disturbance rejection control. Sorry. I believe so far we have acquired sufficiently knowledge on the importance of ensuring robustness of a control system's network towards unknown inputs. It could be a physical disturbance or maybe an cyber attacks. So to ensure high degree of robustness or resiliency of a control system, feedback control system, whether it is a cyber physical network or any simple control systems, the robustness is required to be achieved at the end of the designs. Now, in the yesterday's lectures also, it was presented that the feed-forward control schemes help us to improve or to increase the disturbance rejections ability of any closed-loop control systems. I like to mention at this point that although we all are well aware of this fact, control systems comes into the picture only when the system is subjected with the disturbances. If there is no disturbance in the real-time applications or any systems, which is an idealized assumptions because we all a real world and all the real-time systems are subjected with disturbances. So that implies the requirement of the control systems or a controller in the operations of any physical systems. Now, the controller, yes, it has to be designed to ensure the stability, but at the same time, the controller must ensure the disturbance attenuation ability of the overall feedback systems. So, for examples, just ignore this component, whatever is marked over here. Simply, you have a process, the feedback control system process, whose output is sensed and measured by the sensor, and then it is fed to the controller, and the controller is also getting some reference command from the user. It could be a fixed command or maybe a command which is changing with time. Till now it is okay. Now what we are assuming that in the due course of operations, this process or the plant is experiencing some disturbances. So there are two ways through which this disturbance, the effect of the disturbance to the output of the systems can be compensated. Number one, if we can measure this disturbance directly, and this measurement, suppose you are having a measurement component over here, a sensor through which you are directly measuring the disturbance, and this knowledge is passed to the controller to make it intelligent, so that when this disturbance comes to the process, this controller can easily compensate the effect of the disturbance. This is the first practice, or rather it is the one of the excellent approach through which the disturbance compensations ability can be achieved. But the problem is that this disturbance is characterized as a unknown uncertain component. It is beyond the user knowledge. User is not having any knowledge what kind of disturbance this process is going to face. So something which is unknown, and designing a measurement device to have a good measurement of those unknown component is practically a tedious task. So what we used to do, let the process is experienced with the disturbance, then we design a observer over here, what is called as a disturbance observer, which has a similar type of structure of the process. This observer estimate this unknown disturbance, and this estimations is augmented to the control law to increase the disturbance attenuation's ability. So before we have only a control law in the form of u of t. Suppose I am dealing with a state feedback controller, so u of t, let it be k of xt. While this disturbance observer was not there in the system, now with the help of disturbance observer, we have added one more component in this control law, what is called as d hat. While d is the actual is disturbance coming to the plant, and d hat, let it be the estimated value of the disturbance. This estimations is the output of the disturbance observer. So while you are augmenting this estimated disturbance to this control law, that means you are refining the control law, or you are reaching the control law. You are making your control algorithm to reach, so that when this disturbance comes to the process, it can easily compensate this effect. I'm using the word compensation because complete rejection is not possible, because you are dealing with an observer or an estimator. So at least we can compensate the effect of the disturbance, so that the minimal disruptions of the output or the process variable can be ensured. That is the fundamental idea of, or a fundamental idea behind the designs of active disturbance rejection control algorithm. So you can have a different types of ADRC architecture or ADRC structure in the literatures. Some of the ADRC are defined with a linear differential equations. You can have your non-linear ADRC. You can have your extended disturbance observer, whose advanced version is the generalized extended observer, unknown input observer, etc., which are, or rather which require the knowledge of the system model, or you can call it this type of ADRC are the model based ADRC. I repeat, I guess it is somewhere here. You can see this is the linear ADRC. So this is the schematic representation of a linear ADRC. Here you have a actual process. Here we have designed the extended this state observer, which has a similar kind of dynamics of the process or a plant, but the differential equations through which this linear state observer is demonstrated is a linear differential equation. It is not a non-linear differential equation. We also have a non-linear differential equations type of thing. So as you can see, this is the dynamics of a linear ADRC. It's a similar structure of the Leuenberger disturbance observer, which rely on the dynamics of the plant or the process. Then we have a nonlinear disturbance observer also. For examples, here you can see this is a nonlinear disturbance observer dynamics. Why it is called extended? This E word, E stands for extended. Here, as you can see in these differential equations, that this Z is the state of the observer, the internal state of the observer. If you recall the Lyapunov state observer, which has a similar type of differential equations, correct? So Z is the state of the observer, and based upon this knowledge of the state, we are estimating the disturbance through these linear equations. So d hat is the estimated value of the disturbance. And what is different in this case? Here, not only the d, even we can able to estimate its first derivative also. That makes the sense why it is called an extended disturbance observer. Not only the states, the second state d hat is also, d hat dot is also computed with this differential equations. That's actually defines this E extended, because as much as information you have in your hand and you are able to make your control law reach, that actually helps you to compensate the disturbance in the real-time operations more smoothly. So that actually requires the knowledge of the disturbance estimations or the requirement of the ADRC in the real-time applications. So this is the mathematical description. Actually, in this differential equation, if you can see that the differential equation of a nonlinear system is characterized with equation number 15, which actually having a d component in the first state, and this d has a two component d1 and d2. So in this exercise, both d1 and d2 are estimated with the help of extended nonlinear disturbance observer. So that's why two differential equations 16 and 17 are defined in the same line. In the 16, we estimated the d1 hat and d1 hat dot, and in 17 we have estimated d2 hat and d2 hat dot. And since then the stability analysis is very important. So here we have performed the stability analysis, or you can call it as we have ensured the boundedness of this estimations error with the help of Lyapunov approaches. So this is the estimations error of the first the D component, and this is the estimations error of its derivative component. And we have performed the Lyapunov analysis, although it is not given in the slide, but this is there in the literature. One, if you want to get more idea, you can refer to it. So here we have taken a simple examples. So in the state, we have taken a disturbance which is a sinusoidal type, and in the second case, we have taken a cosinusoidal type of disturbance. We have designed a state feedback controller, which which is something like this, and we also have designs the observer, because it is a Lyapunov observer, the same dynamics it has. So 2 cross 2, as the system has a dynamics of 2 cross 2 and two disturbance component that we are estimating. So the dimension is of course 2 by 2 in the case of K and L. Then you can see here that this is the plot of a robot manipulator systems. A simple robot manipulator system has been single degree of robot manipulator system, in which the positions and the velocities are assumed to be the states. So this is the results. As you can see, with the help of ADRC, we have achieved. And here is the estimations of the disturbance component. So blue one is the reference one, the reference type of disturbance which is applied to the respective joint or the respective differential equations part. And the green one is the estimated one. As you can see that our disturbance observer is capable of smoothly estimating the actual signals, although some estimations error is there, but yes, this estimations error is sufficiently small. So that actually ensures the applicability of its of this type of ADRC in the real-time operations. Yes, by further tuning of the controller, observer again, this estimation error, the value of the estimation error can be minimized. So this is the control effort. So normally the sliding mode control has been used in this case so as to ensure the stability of the robot manipulator systems. So as you can see here, the two different comparisons have been made. One is with the linear disturbance observer and another one is the extended non-linear disturbance observer. So with the extended one, with the non-linear disturbance observer, the disturbance rejection ability is greatly increased uh, compared to the linear disturbance observer. And this is the control effort, the SMC control effort and integral sliding mode control actions was designed. So as you can see that by nature of the sliding mode control, it's subjected with the chattering. Because why it holds the chattering? Because I started with the ellipsis continuity property. If you refer to the design of a sliding mode control, as mentioned in the yesterday lecture, also two important steps are to be followed. One is the design of the sliding manifold and the development of the control law. Uh, since we are interested to increase the robustness of the controller with the help of sliding mode approach, we are introducing some discontinuous term in the equations. And because of this discontinuity of the sliding surface, which violates the ellipsis continuity at s equal to 0, then that makes the sense the control law will suffer with high oscillations, which is known as the chattering. And this leads to a practical problem of the sliding mode control. And to account for this chattering issue, different advanced schemes are also reported in the literature, and I believe in the subsequent lectures by the experts, those advanced component of the sliding mode control algorithm will be addressed, and we will get more ideas about the chattering phenomena and how this chattering phenomena can be accounted by modifying the sliding surface or by enriching the control law in your designs. So with this, I'm concluding over here. So now the session is open. We left with 3 minutes. Now the session is open and I can take a few questions from the participants' ends. There is no questions or queries from your sides? Yeah, please, Kriti Srivastav, you can unmute yourself and you can place your questions. Kriti, please unmute yourself. Kriti Srivastav, you
Sorry,
raised
sir.
your hand. Please unmute yourself. Yes, please, please.
Sir, I wanted to ask about the input state stability in the stability notions part.
Okay. Actually, what it says, for any kind of inputs, because normally what happens, we whatever the Bibo stability we talked about, it is it is actually showing the stability with respect to the bounded input and bounded output, reference input you were talking about. But input state means any type of disturbance that you are giving, because the disturbance is also treated as a states while you are talking about an ADRC. So any type of states inputs you are giving as and considering as a disturbance, and at the end, if you can ensure the stability or boundedness of your signals, so that actually defines the ISS stability notions. The formal definition is there. I have not gone through the formal definitions, but the idea is this: for any type of inputs you are having in your plant, and at the end, if you can ensure, then this ISS stability can be guaranteed. Mostly while we design, one thing which I may forget to mention in my presentations, that you are using the same communication channel for transmitting the measurement as well as control data, either in the cyber layer or in the physical layer. But you are restricted with certain communication resources. The communication resources is limited to us, because if I increase the bandwidth, so obviously the cost of this communication medium will proportionally increase, or increases or whatever be the rate of increment. So we are limited with the limited communications resources. So what we used to do, instead of time series data transmissions in the either sides of the CPS environment, what we did, we transmit the data in an event series. So while you go for the event data analysis, mostly this ISS type of stability you need to confirm, because you are considering a delay in the input states and the subsequent states. So in that situations, for performing the qualitative analysis, this ISS stability is to be guaranteed. So whatever the network assisted control framework you are designing with the event trigger strategy, in that cases, ISS stability is to be ensured.
Thank you, sir.
Any other queries? Any other queries? So I can give you the formal definitions of the input to state stability also. What this says, a control system is said to be input to state stable if it is globally asymptotically stable in this absence of the external inputs, and if its trajectories are bounded by a functions of the state size for a sufficiently period of times. So that way you can define the ISS stability. This is the answer. Formal definitions of the ISS stability as asked by Kriti. So if there are no queries, we can conclude the sessions over here. The next session will start at 4:30. The participants can join through the same link which was shared in the schedule. Thank you all.